can see my screen.
Yes, you can move to, oh, okay. Move to, okay. We are having our last talk on of the highlights of algorithms about spanoids, and that's new creatures that Sivakanth Gopi will tell us about them. So that appears in the ITCS conference. And Gopi, you're welcome to start.
Yep. Hello, everyone. Can you hear me fine?
Yeah, very great.
Yeah. So thanks for the invitation, and thanks to the organizers for organizing this conference despite all the difficulties and uncertainties. Especially want to thank Yossi for being very patient and prompt with all the correspondence. Okay, so let me start. So I'll talk about spanoids. So these are an abstraction of spanning structures. Oops, so these are abstraction of spanning structures that come up in many places, and we studied them because of a particular motivation, which is an application to locally correctable codes. But as we'll see, these are much more general objects, and so hopefully you'll find them interesting. I'll also talk about the specific application that we had in mind. This is joint work with Zev Dvir, Yuzov Gu, and Avi Vidkerson. Okay, so what are spanoids? So spanoids are, you should intuitively think of it as, you have some set of basic rules which you repeatedly apply, and somehow you understand how a system evolves or how information spreads in a system. As you can, this is just an intuitive understanding. You start with some basic set of rules, and then how you understand how some information spreads in a network. Okay, so let's start with some examples where this kind of phenomenon happens. So in gossip spreading or percolation, so let's say there is some graph, or there's some graph with many vertices, and each vertex corresponds to a person, and and the edges corresponds to friendship, let's say. And then you want to spread some gossip through the entire network, and then you want to ask, and then the rule is that if a vertex, or if a person has at least our friends who are convinced of this gossip, then this person also starts believing it, and so on. And then you can ask, what is the minimum number of people that I should convince initially so that I can convince the entire network, and so on. And then there is, for example, logical inference systems where you have a set of statements S1 to Sn, and you have some basic inference rules of the form, a set of statements imply another statement. So for example, S1 and S3 implies S2, and so on. And then you could ask, what is the minimum set of statements which I need to prove everything? So here S1 and S3 will span everything. And another example is linear algebraic span, where you have a set of vectors and you want to understand. And then the notion of span is like your set of vectors span another vector, and so on. And you could ask, what is the minimum number of vectors which span everything? Okay, and there are many examples where this kind of phenomenon happens. So let's define this spanoid more abstractly. So the spanoid it's a very simple object. It's just a collection. So a spanoid S over a set N is just a collection of basic rules of the form a subset A spans an element I. So, and you read it as A spans I. And so it's just a collection of basic rules like that, which you can repeatedly apply to do more complicated inferences. And there's a notion of inference or a derivation. And we say that a subset T derives or spans I if you can derive I from T using a series of basic spanning rules in S. By the way, please ask questions if something is unclear. Okay, so here, for example, like you start with some set T. Inside it, you'll find some subset A naught, which spans I naught. So now you add I naught to your set T. And then you repeat, you'll find some other subset which spans I1, you add I1 to your set, and you go on and finally until some subset in your known set spans I. So this is called a derivation of I from T. Okay, and then the span of a set is just everything that can be derived from set T using repeated application of this basic rules. And then the rank of the spanoid this is an important definition, is just the minimum subset that you need to start with, which spans the whole thing. using these basic rules again. Okay, so the rank is a very interesting interesting quantity that we would like to understand about spanoids in many situations. So let's do an example of a spanoid. So it's called we call it the pentagon spanoid, which comes up again in the talk. So it's called so what is this pentagon spanoid? So there are 5 elements, 1, 2, 3, 4, 5, and the inference rules, the basic inference rules are as follows. The vertices on an edge span the opposite vertex. So 3 and 4, I think I should, do I have a laser pointer here or something? There's an annotate.
We see the cursor when you move it. You can use.
Oh, okay, cool. Okay, that should also work. There is a spotlight. Oops. I thought there was, okay. I think the cursor is fine, yeah. So here you can see that 3 and 4 span 1, and 4 and 5 span 2, and so on. So there are 5 basic inference rules. That's the spanoid. So the rank, so what is the rank of the spanoid? You can convince yourself that the rank is 3. Any 3 adjacent vertices will span the whole thing. And then any 2 of them will not span the whole thing. So 3 is the rank of the spanoid. So any 3 adjacent consecutive vertices will span the whole thing. So for here, for example, I take 2, 3, 4, 3 and 4 span 1, and now 2 and 3 span 5. So that spans the whole thing. Okay, so, and then let me also talk about a little more. So examples where such things arise. So in matroids are another system where you can have the notion of a span. In fact, matroids are, so spanoids are more general than matroids. Matroids have a little more extra structure which capture the notion of span in linear algebra. But you can think of them as spanoids. And then they also show up in point line instances where you can think it's like Sylvester-Galai type theorems. And then finally, there is this notion of union closed families, which show up a lot in combinatorics. So these are just a collection of sets which are closed under union. And in fact, turns out that they are equivalent to spanoids. So spanoids are just a different perspective in thinking about or understanding union closed families. And of course, spanoids also show up in locally correctable codes, as I'll just show now. So what is a locally correctable code? So a Q-query locally correctable code is the following. So it's an error correcting code which has this special properties. So say you have some code word and it gets corrupted. It gets corrupted in a constant fraction of indices, so delta fraction of indices. It gets corrupted, this red regions. So, and I want to find the ith coordinate of this code word. So I want to find u sub I. So I can't just read it off from the code word because the index that I want might be corrupted. So what I do is instead give it to an algorithm called a randomized algorithm. It's called local corrector. What it does is it takes the index I that I want to correct, and then it makes some Q queries at random, not uniformly random, but with, there is some correlation between these queries, and it depends on I, but it can be a randomized algorithm. It makes some Q queries, and based on this Q queries, some of which it can be reading some, corrupted things, but it makes some Q queries and it'll output the UI, the correct index with high probability. Okay, so this is called a locally correctable code. It is called local because you're only reading very few information. Like, to correct the ith index, we don't need to read the whole thing and then decode the entire code word u. Instead, we are just reading some small number of other coordinates to decode the ith coordinate here, or correct the ith coordinate. So these are called locally correctable codes, and they show up a lot in many applications. For example, they're implicitly first constructed in PCPs. In constructing PCPs, these codes are extremely useful, and then they're related to many, many other things. They're useful in hardness amplification, private information retrieval, to name a few. So, and then the question that people are most interested about these codes is like, what is the best possible rate that you can get for a Q-query locally correctable code? So instead of studying rate, let's study dimension, which is the same thing. So which is the dimension of a code is the log of the number of code words divided by log of the alphabet size. So that's the dimension. So we want to maximize, what is the maximum dimension of a Q-query locally correctable code? That's the question that we want to understand. So before we go further, let's try to think of a different way to think about Q-query LCCs, which brings them closer to Spanoids. So intuitively, what happens is, so we want to be able to correct the ith coordinate even when there are lots of corruptions. A constant fraction of these things are corrupted. So what this means is, okay, my local corrector can only look at Q locations at a time, and I hope that maybe these are not corrupted. So what this means intuitively is that the information about UI should be spread somehow evenly throughout the entire code word. So it cannot be just concentrated in a small region. Let's say it's just concentrated in this region, then an adversary can just corrupt that region, and there is no way for me to recover the ith coordinate. So this information should be spread more or less uniformly throughout the entire code word, and this can be captured, you can prove formally that this definition implies the following. It implies that every coordinate I we should be able to decode any coordinate I from a linear number of disjoint Q size subsets. So there is for the coordinate I, there is the subset A1I, A2I, and so on, AI omega of n. So there are linear number of them. Each one has size Q, such that each one will individually will be able to, if we know the coordinates in the subset A1, then we can know the ith coordinate, or A2 will know the ith coordinate, and so on. Okay, so these are a lot of local dependencies that needs to be there in the code for us to be able to do this local correction. So, and you can show these are equivalent, especially for linear codes, it's very easy to show. Otherwise, it needs some work. So far, let's take this as our definition. So, which is that, we can think of a locally correctable code as, a code where for every coordinate in the code that you want to correct, every coordinate in the code, there are this linear number of disjoint subsets of size Q, which each individually can determine this coordinate. Okay, so this is an alternate definition. So we'll come back to this. Why thinking about this is like, so this is, you can see that this is almost like a spanoid. These are your basic rules that each Q size subset implies this element I is the basic rule that you should think of in your spanoid. So what are the best known bounds on this Q-query LCCs? So for two queries, the best known bound is logarithmic. So we can show that the dimension of a two-query locally correctable code is log n. So it has to be very small. So it can be up to n, but somehow just imposing this locality. So if you just want an error correcting code, you can have dimension which is omega of n and correct a constant fraction of errors. But imposing locality imposes a lot of costs. So the dimension can be at most log n. And you can also show that this is tight. You can construct a code called the Hadamard code, which actually achieves this. It's a two-query locally correctable code, which dimension log n. So once Q is at least 3, things get very murky. So Q-query LCCs, when Q is at least 3, the best known upper bounds are due to Iceland and Samoroditsky, and they give you n to the 1 minus 1 over Q minus 1. So this is the best upper bound that we have. So it cannot be linear dimension, but it can still be like polynomial in n. That's the upper bound at least. Whereas if you look at the best lower bounds, the best lower bounds are achieved by Reed-Muller codes, which are polynomial. You evaluate a low degree polynomial or all points on a finite field, and those are the best constructions we know, and they only achieve a dimension of polylogarithmic in n. So as you can see, there is a huge gap. There's the best upper bounds are polynomial in n, and the best lower bounds are just logarithmic. And this is the situation still. We don't know how to close this gap. And the people suspect maybe Reed-Muller codes are the optimal codes. I also believe somewhat that, at least for constant queries, that Reed-Muller codes are optimal, but it's just a wild guess right now. So, and the proof of this upper bound of Iceland, Samoroditsky, and all the upper bounds, even the log n upper bound here happens, all these proofs work as follows. You show that once you have a code, you can always find a small subset of coordinates from which you can infer all the other coordinates. And therefore, the dimension of this code can be at most the size of this subset A, from which you can infer everything else. So for example, for a two-query LCC, you can show that there is a log n size subset from which you can infer everything. And similarly for Q-query LCCs, you can find a subset of size this n to the 1 minus 1 or p minus 1. So in other words, what these upper bounds are doing there are implicitly proved by bounding the rank of an associated spanoid, right? That's how all these upper bounds are shown. So let's study the spanoid, the associated spanoid, which we call a locally correctable spanoid. So basically, it's a spanoid on n elements where you add this basic rule. So remember that in a Q-query LCC we had this structure theorem that any coordinate I should be able to decode from these disjoint subsets, any of the disjoint subsets of size q, and there are linear number of them. So we add all these basic rules into our spanoid. So we'll add AI1I, AI1 implies I, AI2 spans I, and so on into our spanoid. So there will be roughly like omega n squared rules, basic rules. For each coordinate, we have omega n rules. So we call such a spanoid a Q locally correctable spanoid. And we are interested in understanding what is the rank of such a spanoid is. Okay, and of course, the dimension of a Q locally correctable code can be at most the rank of the associated spanoid, just because of the same reasoning that if you have a small subset of size the rank, which implies everything in the spanoid, it means that in the code itself, a small subset of coordinates implies every other coordinate, and therefore the dimension of the code can be at most the rank of the spanoid. Okay, so we want to understand what is the best rank possible for this locally correctable spanoid. So recall that the best upper bounds and lower bounds are very far apart. At least when Q is 3, the best upper bounds are polynomial and the best lower bounds are logarithmic. And the best upper bounds are proved by bounding the rank of a spanoid, upper bound in the rank of associated spanoid to the LCC. So here's our main barrier result. We show that the upper bounds of Iskelen and Semeroditsky, which is this polynomial upper bound, cannot be improved using the spanoid rank approach, which means that so all the current upper bounds are kind of stuck using this method that you try to find a small subset which implies everything else. And what we prove is that such an approach cannot work. You cannot improve this upper bound. And we prove this by actually constructing a Q locally correctable spanoid whose rank exactly matches this bound here, this upper bound. So this is a barrier result saying that if you want to improve the best upper bounds known, you need to go beyond this simple method of finding a small subset which implies everything. Okay, so it's not all negative news. We also have some positive news where we also show a new approach to improve the upper bounds. We have seen that this rank approach cannot improve the upper bounds, so there is a barrier here. So we give a new approach by, we can show that you can upper bound these dimensions using another notion. Instead of the rank of the spanoid, we define a new notion called a functional rank of a spanoid. And by studying this quantity, we can actually improve the upper bounds here. Well, we can hope to improve the upper bounds here. So what is this functional rank? So the functional rank of a spanoid is defined as follows. So you look at, so let's say we have some spanoid S on n elements. So you define, we say that a code C is consistent with the spanoid if whenever you have a basic rule A spans I in the spanoid. That means that for every code word in C, you should be able to determine the ith coordinate from the coordinates in A. So UI should be able to determine as a function of just the U restricted to A. So this is what a code, this is the definition of a code which is consistent with the spanoid. So it basically means that, the code, the inference rules of the code is consistent. Like every inference rule in the spanoid implies that, gives you an inference rule in the code, which tells you that these coordinates determine this coordinate here. And you define the functional rank of a spanoid to be the supremum of the dimensions of all codes which are consistent with the spanoid. So is that clear? So it's just so you look at all the codes which are consistent with the spanoid and you take the best dimension, the supremum. So there are lots of interesting things here. So firstly, this F rank need not be integral. That's because the dimension need not be integral. It can be fractional. Moreover, it can happen that this may not even be attainable, in the sense that there is no single code which will attain the F rank. You can have a sequence of codes which get better and better F rank, and with it, but the limit is something, but it is not attained by any specific code, because this is not really a compact set that you can take a limit. And it's not even clear it is computable. So this is a very mysterious quantity, this F rank. And that is the thing that we should be upper bounding. That is the interesting quantity for a spanoid. And naturally, the functional rank is upper bounded by the rank, because any code which is consistent can have dimension at most the rank of the spanoid. So this is an obvious upper bound, but we want better upper bounds on the functional rank, which is better than the rank. So how do we do it? How do you upper bound this? So in other words, to break the barrier that we proved, you need to upper bound, you need to be able to prove upper bounds on F rank which are better than rank. And how do we do that? So let's look at a small example which we started with, which is this pentagon spanoid. So what is the functional rank of the simple spanoid? So recall that the rules here are that vertices of an edge imply the opposite vertex. So you see that the rank is 3. So here is a code which shows that the functional rank is at least 2.5. So the code is defined as follows. For every x in 0, 1 to the 5, you put 2 bits on each vertex. So on vertex 1, you put x2, x5. On vertex 2, you put x3, x1, and so on. And now you can show that this code is consistent with the spanoid rules, because what is this? So this spanoid rule, this 3 and 4 should span 1. So therefore, x2 and x5 we should be able to guess if we know the values of x5, x3, and x4, x2. But that is very simple, because it's just, you can just read it off, x2 from here and x5 from here. And similarly, 2 we should infer from 4 and 5. So 3 and 1 are present here, so you can infer them. So take 1 bit from here, 1 bit from here, we get this, and so on. So this is a valid, is a code which is consistent with the spanoid. And its dimension, as you can see, calculate explicitly, is the log of their 2 to the 5 code words, and the alphabet size is 2 squared. So therefore, it's log of 2 to the 5 divided by log of 2 squared. So it's 2.5. Okay, so we have constructed a code which is 2.5, but how do we know if the actual F rank is less than 3, or maybe there is a sequence of codes which can take you all the way to 3. So how do we break this rank barrier? So in fact, we can show that the functional rank of the spanoid is actually 2.5. There cannot be a better code which is consistent with these rules. So this is the best possible code you can have, which satisfies these rules, that from 3 and 4 you can infer 1, and so on. So how do we prove such a statement? What is a better upper bound? And the key is to use entropy. So you can show that you can upper bound F rank using entropies. And in fact, so there is this called the basic Shannon information inequalities, which is the following. It's just the conditional mutual information is non-negative, and the conditional mutual information is non-negative, and the conditional information is non-negative. These things are called basic Shannon inequalities. By manipulating these inequalities, you can actually upper bound the functional rank of the pentagon spanoid, and you will get 2.5. So let's do so you can, in fact, like this might look a little bit arbitrary, but you can make it like a you can write a systematic linear program called the LP entropy of S. So this is just so given a spanoid, you can write a systematic or a canonical linear program which captures the best upper bound you can derive on the functional rank using this basic Shannon information inequality. So I'll show you what this linear program looks like. It's not very complicated. You might ask, like, why should I stop? Aren't there more inequalities that we can put on the entropies? So in fact, there are more non-trivial inequalities on the entropies. These are called non-Shannon inequalities. The first one was found by Zhang and Young in '98. So, almost 50 years after Shannon discovered these inequalities. So there are non-trivial relationships between the entropies, but these are very poorly understood, and we don't really know how to systematically enumerate all of them or do anything with them. But but we can only work with these basic inequalities. And there is a nice and succinct way to capture all the basic inequalities, Shannon inequalities. So in fact, like everywhere you see information theory and computer science, everywhere it is used to prove maybe communication complexity lower bounds or anything, people only ever use the basic Shannon inequalities. Nobody ever used non-Shannon inequalities. So these are like really very powerful already to prove many interesting things. Okay, so what is this entropy functional? So we have seen that if there is a code consistent with S, so then we can define a random variable X, which is a uniformly random code word of C. And then we define this entropy functional little h, which takes a subset A, and then it outputs the entropy of X restricted to A, and then normalized with the log of the alphabet size. This is just a normalization condition. So it's basically the entropy of X, this random code word, restricted to the subset A. That's what H is. And then Shannon showed that H is a monotonically increasing submodular function. This is the crux of the Shannon inequalities. So the basic Shannon inequalities are equivalent to the fact that this H is a monotonically increasing submodular function. And of course, H of 0 is 0, and H of indices is at most 1 because of the normalization here. And then this is where we capture the spanoid rules. So if A spans I in the spanoid, then it implies that H of A union I should be same as H of A. That's because, you know, this I, X sub I, is determined by the X in the indices A for every code word. Therefore, there is no more information in A union I than just A. So this is an equality. So using these extra equalities and the inequalities given by the submodular function, you can derive upper bounds on the entropy of the whole set N. Okay, so all these things can be succinctly written as a linear program. So the functional rank is upper bounded by the following linear program. You minimize over all f of the whole set, where the minimization is over all non-negative functions, which are monotonically increasing submodular functions. So this is a set of linear inequalities. And then you have the following inequalities, which is f of 0 is 0, f of I is at most 1. And then all the spanoid rules give to the following equalities, which is that whenever A spans I in the spanoid, then you force f of A union I to be f of A. So this is a linear program, and this captures the best upper bound that we can prove on F rank using the Shannon information inequalities. Okay, so this quantity, which is the value of this linear program, sits between the functional rank and the rank. And in fact, for the pentagon spanoid, you can explicitly calculate the value of this LP, and it actually turns out to be 2.5. So that's how we know that the functional rank of this pentagon spanoid is 2.5, because we have a code which matches this, and they have an upper bound. So in general, there is no proof that, you know, this will match exactly with this. So it is strictly a relaxation. Okay, so now you could ask, like, okay, so you have this rank and F rank. Can they be very different, or should they always be close? Okay, this is an interesting question. So we've seen in the pentagon spanoid, they can be different. They need not be equal, but can they be very far from each other? So this is our main result too. We show that, in fact, this LP entropy functional itself can be very small compared to rank. So it can improve the upper bound on F rank by polynomial factors. So there exists some spanoids. We construct some explicit spanoid where the functional rank and the LP of entropy LP is at most rank times rank over some polynomial in N. So what this shows is that this LP entropy is actually, much better upper bound on F rank than the rank. Can be like, up to polynomial factors. So this gives us hope that maybe we can improve the best upper bounds on locally correctable codes using this entropy function rather than using the rank. So, so we have the following challenge, which is still open, which is that is there a spanoid whose functional rank is really small? Like, can it be n to the little 1, whereas the rank is polynomial in n? Can there be such a thing? So Q locally correct, this Spanoids which occur from Q query locally correctable codes are obviously candidates for such a Spanoid, but we don't know if there is, if their functional rank has to be so small for such things. But if you prove that there are no such Spanoids, whenever the rank is polynomial in n, the f rank should also be polynomial in n, you're indirectly proving that there are really good Q query LCCs whose dimension is polynomial in n. So that would be very surprising if that is true. So either way, I think it would be an interesting challenge to solve. So let me conclude. So we show that Spanoid rank is a barrier for beating the existing LCC bounds. And we actually give an approach to break this barrier using Shannon entropy. And we give a linear program which possibly can give a better upper bound. And we have instances of Spanoids where it improves it polynomially. And another interesting thing is that because it's an LP and you don't need to exactly calculate the LP, you can give this is a minimization LP. So you can give an upper bound on it by, so by LP duality, right? By LP duality, you can get upper bounds on the LP entropy using feasible solutions to the dual LP. And of course, Spanoids by themselves are also very interesting. I think, people, there's a lot more happening, a lot more things to study. They occur in many diverse areas, and I think they're worthy of independent study. Especially this relationship between rank and F rank seems like a very interesting question. Thank you.
Okay, thank you, Gopi. And questions, you please write it in the chat. So while people are thinking, let me ask, is it clear the rank for, if you're given a specific Spanoid, finding the rank, is it NP complete or it's polynomial time?
It is NP complete, yes.
It's NP complete.
Yeah,
like
finding
it's
the rank
even harder than set cover? I mean, is it harder than set cover?
I mean, yeah, I think there is a reduction to set cover through set cover, yeah.
Mm-hmm.
It's in our paper. It is NP complete, yes.
Yeah, it's also hard to approximate.
Oh, approximations, I don't know, but calculating exactly is hard. I don't know if it's hard to approximate as well.
And what about the F rank?
F rank it's not even clear it's computable because it's a limit of some infinite set of objects. So we can only prove upper bounds and lower bounds on it. It's a miracle that we can actually compute it even for the small Spanoid, the pentagon Spanoid. Mm-hmm. In general, it's hard. I don't think it's even computable. Yeah.
Mm-hmm. Okay, more questions? Okay, so again, if anyone has still more questions, you are welcome to use the Slack channel later. And this is it. The highlights of algorithm is over. I would like to thank again everyone that helped, especially Moses.